Many assume that deep learning algorithms are mathematically objective because their outputs are driven entirely by quantitative rules. In practice, however, these systems consistently produce subjective and discriminatory outcomes when applied to real-world tasks. This visualization maps commercial facial recognition performance. Current data shows a massive performance gap. These models misclassify women and people of color at rates up to 30% higher than white men. These performance disparities occur because neural networks are designed to optimize for specific patterns found in their training environments. Models optimized strictly for mathematical accuracy on historical data will inevitably encode the structural inequalities present in those records. Algorithmic bias is an architectural property of neural network optimization. It is an inherent characteristic of how these systems weight information. To address this, we must analyze the internal layers of neural network computation and pinpoint the specific variables where human bias enters the math. Our investigation will track the mechanics of artificial neurons, examine how they scale into massive architectures, and break down the technical pipeline required to manage them. Mapping this mathematical architecture provides the foundation for engineers to develop active interventions that can mitigate these harms. All deep learning models are constructed by stacking layers of artificial neurons that transform input data into a final prediction. This diagram shows a single artificial neuron. Data inputs, labeled X, arrive through connections that apply a weight. This weight is a numerical dial that controls how much influence each specific input has on the final decision. The neuron adds a variable called a bias, which acts as a threshold that shifts the neuron's activation point regardless of the incoming signals. Finally, the neuron passes the result through a nonlinear activation function. This step is what allows the network to model the intricate, nonlinear relationships found in real-world data. Stacking these neurons creates a network, but for that network to learn, it must be able to recognize its own errors. This is handled by a loss function, which calculates the exact mathematical difference between the network's prediction and the actual target label. In a process called backpropagation, the network sends this error signal backward through the layers. An optimization algorithm called gradient descent uses that backward signal to adjust every weight and bias, incrementally tuning the parameters to minimize the loss function. The system repeats this process millions of times until the mathematical error reaches its minimum. Because the network's only goal is to reduce that loss value, it remains entirely indifferent to the social implications of the data it is optimizing. Simple networks cannot process high-dimensional data like images or voice, requiring more specialized scaled architectures. For computer vision, the industry standard is the convolutional neural network, or CNN. This animation illustrates how a CNN uses filters and pooling layers to extract a spatial hierarchy. It identifies basic edges and shadows before combining those features to recognize complex objects. Sequential data, like human language, requires a different architectural strategy. Transformers process entire sentences simultaneously using attention mechanisms, which mathematically link words based on their context within the whole sequence, rather than just their order. These mechanisms allow generative AI to capture deep semantic meaning and maintain coherence over long passages of text. While these specialized architectures are highly efficient, their immense scale makes it difficult for human observers to audit exactly how individual features are being weighted. Because neural networks are optimized solely for performance, societal imbalances enter the model at 3 specific structural points. This diagram highlights the first entry point, the input data. This results in data bias. If the training data is imbalanced or contains historical records reflecting past discrimination, the model will ingest those biases as foundational truths. The second entry point is the optimization process itself, creating algorithmic bias. If a loss function optimizes for highest overall accuracy, it will mathematically deprioritize the weights associated with minority groups to achieve a higher score for the majority population. The third entry point is the final deployment, leading to application bias. For example, an AI diagnostic tool trained in one region might fail when applied to a demographic with different genetic or environmental backgrounds. This demonstrates that AI is a socio-technical system. The software cannot be separated from the human environments that produce its inputs and use its results. Because bias occurs at the input, at the optimization, and the application levels, mitigating it requires a multi-stage engineering pipeline. This flowchart illustrates the three-stage pipeline required to systematically mitigate these risks. In the pre-processing stage, engineers use data augmentation and stratified sampling to balance the training sets before the network ever begins its calculations. The in-processing stage involves modifying the model's learning objective to prioritize fairness. Engineers can use adversarial debiasing, where the main network is penalized if a secondary network can successfully guess sensitive attributes, like race or gender, based on its predictions. This forces the loss function to minimize error while simultaneously maximizing demographic neutrality. The post-processing stage occurs after the model generates a prediction, but before that prediction is acted upon. Explainable AI tools are used to interpret the model's internal weights, revealing which specific features drove a high-stakes decision, and allowing engineers to audit the logic for latent bias. Effective mitigation requires these mathematically rigorous interventions at every phase of the AI lifecycle. These mitigation strategies often reveal a difficult trade-off. Implementing fairness constraints can lower the model's absolute predictive accuracy on the training set. Deciding where to strike that balance is a societal and ethical decision. This shows the European Parliament, where regulatory frameworks like the EU AI Act are being developed to standardize fairness measures across the private sector. Continuous monitoring is required because a model's performance can drift as real-world data changes, necessitating regular recalibration of its internal weights. Developing ethical AI requires aligning the efficiency of mathematical optimization with the requirements of human equity.